All right. Well, hello. Monday, Tuesday, Wednesday, Thursday, Friday. Whenever you have to be watching the video, we're going to be going over the January 23rd, 2019 Algebra 1 Regents. All right. I know a lot of you have tried to take the Regents and didn't go so well. And I just want to. We're we're about to have spring break, right? So we're coming up to about a week off. So we're going to approach this Algebra 1 Regents in this week before spring break. And I'm going to try to hopefully, the goal, I'm trying to hope you, to make you see that Algebra 1 Regents aren't so scary. You have the tools to do this. It's just sometimes the Regents ask the questions in ways that are unfamiliar. They try to ask you questions that make you have to think. And once you see how they ask questions, I'm hoping that will be a key to make you successful on these. So we'll get started. I'm going to do this video in three parts as my plan. 8 questions per part, 8 questions per part. And so we will be doing this questions 1 through 8 in this video, questions 9 through 24 in the next video, and then questions 25 through 32 in the third video. And so we'll start with question number 1, all right? January 2009, let's begin. I've got the lesson set up today, or all this week, is for you to pick one question that's easy for you to do. So you pick one question that's easy for you to do, you try to do that problem, and then you show somebody else how to do it. That's step 1 of each one of these lessons. You find an easy one, do it, show someone else. Step 2 is you find a hard one. Find one you don't know how to do. Find someone in the room to help you, whether myself or one of the TAs. And then the third step for these ones, we're going to go over a part 2 or part 3 question. That's how this week's lessons are gonna line up. All right. So hopefully you're not just gonna watch this video. Here's what not to do. Don't watch this video and just copy down all the problems I've done. Hopefully, I mean, if you're not in class, then I mean that's why I'm doing these videos. If you're not in class, really. But if you're in class, I'm hoping you're not watching these videos and just copying what I'm writing, because we need to get your mind activated, all right? We need to get you thinking so that you can do these on the Regents that you're going to be confronted with, right? We'll probably do one more Regents before the end of the year. We'll go through it back to back. We'll probably do last June's Regents. So you get an idea what a June Regents looks like. In my experience, the June Regents is kind of a middle Regents. The August Regents is probably the easiest one often, and then January for some reason tend to be hard. I don't know why that is. This January 2019, it was a hard Regents, or else it was an easy Regent that they made the scoring ridiculously hard because they thought it was too easy. I don't know. Here we go. Question number 1. We're doing our multiple choice. Scatter plot below. This is a scatter plot. All right. Now, I didn't go over scatter plots too much in our Algebra 1 review. It was one of those units we just kind of left off because it's statistics. It usually comes at the end, and there are more important things to do. So this is one where I never taught you how to do scatter plots. Maybe, hopefully, you've seen something like this before on a graph somewhere in science. It's often where scatter plots are used because the data in science is often ugly like this, and we need to use math to make the ugly understandable. We need to make some sense of the ugly data we find in science. This is a scatter plot. The scatter plot below shows the relationship between the number of members in a family and the amount of the family's weekly grocery bill. All right. Let's see what's going on. Here is our y-axis. See how it's labeled y here? Our vertical axis is always our y-axis. I'm having trouble getting the paper to want to lie flat, so I might have to just tear this off. I'm not liking that I have to keep pushing that down. Okay. Here we go. So we have a scatter plot. And let me make sure the camera is focused now that I've changed the height of the paper. All right. Here's my y-axis. You see that? It's that vertical axis. See where my pencil's going? Up and down, vertical. It says grocery bill. So what's the y-axis telling us? It's telling us this is how much their grocery bill is in dollars. Here's what the y-axis is telling you. This is telling you that the y-axis is how much they paid in terms of grocery bill. And then in parentheses here, the parentheses with these little marks that kind of bracket this in, it says dollars. It says that the grocery bill is being measured in units of dollars. All right. Usually we measure money in dollars in the United States, so you should be fairly familiar with that concept. X-axis is the number of family members. So you can have one family member in a group, two family members in a group, three family members, four. So I was going to pick a random one. 4 family members. I have 4 data plots for 4 family members. I have one 4 family member family, and their grocery bill was just over $100. Another 4-member family, and their grocery bill was slightly less than $200. Another 4-member family, and their grocery bill was like $250. And then our last 4-member family in this data, and they had a grocery bill of $300. You see how you read this? Each one of these dots represents a single family unit of different number of family members. So here's our, I guess we have no data for one family member. We've got one family that only had 2 members in it in this data plot. Let's see what the question's actually asking now that we kind of understand what the chart's saying. The most appropriate prediction of the grocery bill for a family that consists of 6 members is it 100, 300, 400, or $500? All right. Well, again, this is statistics, and in statistics, we try to make sense of ugly data that real life usually throws at us, right? And this is kind of a scatter plot is a fairly good representation of how messy real life data can be. And we're going to use math to make sense of it. So again, I didn't teach you much about statistics, but maybe you could make a projection. See if you could think about if you were to run a line through this data, like right in the middle of this data, where do you think that line would be? Pause the video here, take a few seconds to think, what do you mean, Mr. Solt? Where would I put a line that goes right in the middle of the data? Yeah, try to take a straight edge or ruler and draw a line that kind of goes through this data. All right, try that. Okay. Hopefully you unpause the video at this point, and you've already drawn your line. But if you really lacked confidence in your ability to draw lines in the middle of the data, you're just watching, you're waiting for me to give you some guidance. So here I go. Can you kind of see how this data has this like diagonal pattern to it, right? Do you see this? So I'm going to put a line that kind of goes right here. Now, there's actually a way. There's a way to put all this data in your calculator and have it draw a line of best fit. That's what this line is called, a line of best fit. And there's also a way to have a formula that will create the line of best fit after we add up all the sums of these. It requires a lot of button clicking and math that you don't really need for this question. You just kind of have to, you could just eyeball this question and say, I think a line of best fit is probably going to be somewhere in the mishmash of this. Notice how I've got, in fact, I'm not even sure this was the best line. This wasn't the best line of best fit because I have one dot here, no dot below it, but this line's already pretty close. I have 2 dots above my line and one just below it, so that's not the best fit so far. I've got 2 dots above and one on, one below. Okay, that's a little unbalanced, but better. This is better. This is a good line of best fit for families of 5. I'm doing okay here. I got 2 dots above. My line's a little low. If I was to make this a little bit more perfect, I think I'd raise that line just a little bit. You don't have to raise your line. The first line we drew, just kind of boop through the middle data would have been good enough. I'm just kind of giving you this idea of you kind of want the same amount of dots on both sides of your line. Even so, now we got 2 projected lines of best fit. What's the question asking again? What is the most appropriate prediction of the grocery bill for a family that consists of 6 members? All right, let's look for like our number of family members that are 6. There. Notice that we don't have any dots for a family of 6 members. We found some families with 7 members. We found some families of 5 members. But we didn't find any members of 6 family members. They want you to predict, well, what would the grocery bill be for a family consisting of 6 members? Well, take a look at our lines of best fit. This one I kind of drew, which maybe isn't quite as good, went around about the 250 range. And then this line that I drew, which was trying to get more of these dots on both sides of my line, went just right almost through the $300 range. And then let's look at our options we have. I'm looking at an option that for anywhere between $250 and $300. 100, nope. 300, yep, that's pretty darn close. 400, nope. 500, nope. Here's how I answer that question. I'm looking to draw a line of best fit just through the data, right in the middle, and I would select $300 for a family of 6. Um, and that's really all you really need to do to answer that question. That requires you just kind of think and look at the data, try to see what line or where in the middle of here. I mean, hopefully in this data you were saying, okay, maybe somewhere in here. Well, notice that right here is at 300. All right. So this is how we can use statistics in lines of best fit with messy real-world data to find a line of best fit and make a projection where we're missing, or where we have missing or incomplete data. All right. This is the beauty of math. We can make real-life projections that can help save us money and help make future projections. Future projections. There's lots of money in that, in economics, in Wall Street, in weather. There's all sorts of great things we can do, and we can protect the future. We reduce risk. All right. Okay. So, question number 2. All right. Problem 2. Let me read this to you. The function g of x, is defined as the g of x equals negative 2 times x to the second plus 3 times x. The value of g of negative 3 is, so we did this on our functions unit. This notation here, the g of negative 3, tells us to replace every x in our function with the number negative 3. So I've rewritten it over here. G of negative 3 is going to equal negative 2 times negative 3 squared. Just like I have negative 2 times x squared, now I have negative 2 times negative 3 squared, because this is the g of negative 3, plus 3 times negative 3. All right? This next step, I took negative 3, and I remember PEMDAS, we did this in the unit of PEMDAS, we have to use the exponents first. So negative 3 times negative 3, that's positive 9. Now positive 9, I have to make sure I bring this negative down here for the 2. Negative 3 times negative 3, that's positive 9. Or negative 3 to the second power, positive 9. Use your calculator if you don't remember how that works. Negatives times negatives are positives. Negative 2 times positive 9 is negative 18. Positive 3 times negative 3 is negative 9. Now I take negative 2 times positive 9. Negative 2 times positive 9 is negative 18. And negative 18 plus negative 9 can be negative 27. Now, when I first wrote that, I wrote that really quick on my paper, and I forgot to put the negative 2 in here, and so that kind of threw off my first evaluation, as I wasn't hardly thinking. I was just kind of boop, 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 boop. Do that on the Regents. You want to say, okay, if I don't have an answer that matches one of my 4, I need to think about it again. And even if you find an answer that matches one of your 4, go through the problem and say, did I copy everything right? Check all your math. Use that tool of the calculator to make sure everything fits. All right. All right. So we got negative 27. Negative 27 is choice number 1 here. All right. Hopefully that's not too bad for you. You have to know that the g of negative 3 means to plug in negative 3 for every time you see x in the function. Once you do that, you could actually do all of this on your calculator. Let me show you how to do that. Let's see that. Let me get my calculator up here. Okay, here I go. Need to lower it just a little bit. Oh, you can't see it where it's at. All right, let me move it over here. There we go. Now we can see it better. All right. Negative 2, parentheses. These parentheses are important. You can't leave these out because your calculator is kind of, it's a machine, and the machine can't interpret what you intend for it to do. It can only do exactly what you tell it to do. So I'm putting all my negative 3's in parentheses because I want the calculator to know that that's a negative 3 and not minus 3. I want the calculator to know to do the negative, to keep that negative with that integer, all right, with the absolute value of 3. And plug that in. Negative 27. See, if you use your parentheses, if you know how to put in your calculator, but again, you have to know that d of negative 3 means putting negative 3 in for every x, and then you put that in your calculator. And hopefully that one was a pretty easy one for most of you. I don't see that one as being too tough. Number 1 was a little bit more involved because there was statistics, and I didn't show you lines of best fit. But hopefully you might have gotten that from other courses, having taken Algebra 1 with other teachers, when they had a full year to teach it to you. All right, number 3. Which expression results in a rational number? All right. Now this one is a little bit harder. I talked about rational numbers twice, maybe 3 times, but I didn't spend like a whole day on it or anything. I just kind of defined it a few times and we moved forward. There usually are questions on rational numbers on the Regents. I should probably emphasize this more in the future. So if you don't remember, a rational number is a number that has a really nice decimal form, something like 1 or 0.5 or 0.144 or 287. A number that is really nice, that doesn't go on infinitely, right? A number that would not be really nice would be like 33333333 goes on forever, right? Where it's just 33333333. Another number that would not be nice, famous irrational number that we math, oops, let me show it to you on the calculator. The square root of 2. The square root of 2. Oh, that's not, that's not a very pretty number, right? It just keeps going on. It's what happens is this number goes on for so long that we can't really use a number that's that long in a lot of things, which means if we use it, the decimal form of that number, we get an inexact approximation. Like this isn't the complete number that you see here on the calculator. The calculator is rounding after a certain number of, of digits, which it doesn't think you're going to need. The calculator actually has in its memory, it knows that this number is a lot longer. And if I multiplied it by, another square root of negative 2, oh, shoot. If I multiply this by the square root of 2, it'll just give me 2 because it actually calculated the actual square root of 2, even though it didn't show me that it went on forever and ever. So, where was I going with this? We need to find which one of these 4 choices here results in a nice, clean decimal answer. So let's look at this. Square root of 121. Put that in your calculator. Let me put my calculator here. The square root of 121. That's 11. Ooh, 11 is a nice rational number. It doesn't go on forever. Let's see about my square root of negative 21. Square root of 21. Apologies. Oh, square root of 21 gives us I'm going to call this a funky decimal. In mathematics, we call this an irrational number. A number that just goes on forever, and so if we use the decimal form, we're going to get something that's inexact because we can't keep writing forever. So usually we leave these in their square root form. So 11 minus an irrational number is going to give me an irrational number. It's going to be 11 minus 4.5825 that goes on forever, right? Number 1 can't be right. That does not result in a rational number. All right, let's talk about choice number 2. Oh, I need to kick my calculator so you can see it. Square root of 25. Oh, well, hopefully you all know that. Square root of 25 is 5, right? What is the square root, though, of 50? Is that a nice number? No, it is not. That is not a pretty number, right? That's a big, long decimal. That's called irrational. That's not good. If I multiply an irrational number by 5, look at that. I get another irrational number. That is not going to work. Choice number 2 is not going to give me a rational number because I'm taking a rational number. Square root of 25 is just 5. That's rational. Square root of 50, not rational. big, long, funky decimal. Can't uh, limited applications for that. All right, without approximating. All right, square root of 36. I hope we know what the square root of 36 is, but it's okay if you don't. That's 6, right? Hopefully these are basic math facts that we're getting as we progress in this course. 6 times 6 is 36. Therefore, the square root of 36 is 6, right? It's the inverse of the number squared. But what about 225? Now, I don't expect you to know that 225 is a perfect square, but it turns out that it is. And you can use your calculator to confirm that. You can see that 15 times 15 is going to be 25. Let's see that on our calculator. 15 times 15, look at that. 225. Is 6 plus 15 going to give us a nice number? 6 plus 15? Oh, yeah. That's just 21. That's our answer. And that's how you find that one. I could keep going on, but these two here, it's a square root, 3 times the square root of 5, 3 times the square root of 5. And as you can see, that's going to be a funky number. And if I add that to 2 times the square root of 5, also going to give me an irrational, funky decimal that is not a nice, clean answer if I write it in decimal form. Number 3 is our correct answer for question number 3 on the region. Let me think about the difficulty of that. This is a super difficult question if you don't know the definition of a rational number. If you don't know that rational means a nice clean decimal, and you don't know that an irrational number means a funky decimal that goes on forever, then this is going to be almost an impossible question. But if you know that simple vocabulary term, and you have some number sense of, okay, you know, that square root of 36, that's going to give me a nice number. And the square root of 225, I don't know that, I use my calculator. I find that's a nice rational number. Boom. This becomes pretty easy once you have a grasp of the vocab. If you don't have the grasp of the vocab, that one's hard. That one's hard if you don't have the grasp of the vocab. Therefore, we need to learn our vocabulary, right? Okay. All right. All right. Let's do question number 4. I'm tearing it off my Regents, right? Because I didn't like the way it was laying flat. All right. I'm going to move my camera at the risk of blurring it for you. Let's read this question. The math department needs to buy new textbooks and laptops for the computer science classroom. The textbooks cost $116 each, and the laptops cost $439 each. If the math department has $6,500 to spend and purchases 30 textbooks, how many laptops can they buy? All right. Pause this for a minute. Just think. Do you know how to do this? Try something. Pause the video and try something. Don't give up. Don't give up. See if you can write any formula or function at all based on this word problem. You need to be able to look at this word problem, and you need to be able to write out an equation or formula to help you do this. This is the way we go about this one. So pause right now. See what you can do. Well, hopefully you paused and you tried something, right? That's what it's all about. Trying something. Get a few points here and there. This is one of these word problems. A lot of students struggle with these word problems. Let me be honest with you. But the Regents loves them, I think. So let me see what I have. I have textbooks. Cost $116 each. I know that laptops are going to cost $439 each. I know the math department has $6,500 total to spend. And I know that the textbooks plus the laptops. All right, there. So my number of textbooks, I'm going to call the number of textbooks X for a second. Again, I'm just playing around with an equation. Can you see? Let's see. Yes, you can see what I've written. Here's what I wrote down. I mean, again, this is just my beginning thoughts of an equation. This isn't the final form. right? For the Dragon Ball Z fan. 6,500 equals the number of textbooks times how much a textbook costs, because X is the number of textbooks. P is going to be the number of how much a textbook costs, plus the number of laptops times how much the laptops cost. Can I start to fill in some of this information here? You know, in my head, I want to switch this around. I want this to be the number of textbooks. I want this to be how much they cost. I want this to be the number of laptops. I want this to be how much they cost, because I want to keep the T and the L in this equation. I know textbooks are going to cost me $116 each, right? So number of P textbooks times 116. They told me that textbooks cost 116, so I'm putting in 116 times the number of P textbooks. Now for laptops. For laptops, they told me I can put in this number. They told me laptops are going to cost $439. The number of laptops times 439 is going to give me my total cost of laptops. If I only buy one textbook and one laptop, then all I have to do is add 116 plus 439. Does that make sense, hopefully? If I am going to buy 10 textbooks, let me try to see if you can make sense of what I just wrote down here. If I'm going to buy 10 textbooks, I know they each cost $116. I'm going to multiply 10 times 116. That's going to be $1,160 if I buy 10 textbooks, right? We all have this idea that every time we buy a new one, we got to multiply the number of how many we buy times the cost of each one. Okay, hopefully we're pretty good with that. Now I have an equation with two variables. I have two variables, and I can't solve this equation the way it sits because I have one equation and two variables, and that's not enough information to complete an equation. Keep looking. Pause here and see if you can do anything with this from here. Read the question again. All right, pausing. Okay. Hopefully you figured this out. If you're stumped, it's okay, right? That's why we're doing this review. The information, when you reread the problem, you did read the problem, didn't you? It also gave me information that if the math department has $6,500 to spend and they purchase 30 textbooks, purchase 30 textbooks, I can put 30 in here now. P is the number of textbooks. I know they're going to purchase 30 of these things. So I'm rewriting my equation a little bit. All right, I basically rewrote my equation because now I know we're going to buy 30 textbooks. So let me see what 30 times 116 is. 30 times 116, that's 3,480. So I know this is going to be 3,480 plus L, 439, equals 6,500. And I'm running out of room. Notice I'm running out of room on this particular problem. That's okay. And you can write all over your test. You can use scrap sheets of paper. We'll see if you can have accommodations for scrap sheets of paper. And there's on the back of the test, there's also a blank sheet of paper if you run out of room. Now this equation, I'm hoping you can solve. We've done a lot of these. This is just an equation with a variable times a multiplier or times a coefficient, right? And then what do we want to call this? I'm struggling with this vocabulary. A constant. There we go. This is our constant, and this is our output, right? So I'm going to subtract. I'm going to subtract our constant first. Now the numbers here are big. But the techniques don't change, right? If I subtract the same amount of money from here, then these two cancel. I can ignore the 3,480 on this side of the equation. But if I subtract it from this side of the equation, I gotta subtract it from this side of the equation. Again, I'm going to use my tool. I'm not going to do all this in my head. Minus 6,500 minus 3,480 is 3,020. 3,020 equals the number of laptops times 439. Okay. Now I'm going to divide by 439 on both sides. I'm going to divide by 439. 439. Bringing my calculator back. I want to divide by 439. And I get 6.87. All right. I'm going to in my box here. L equals approximately 6.87. All right. So I've isolated my variable. Make sure you can see. Yes, you can. Nope, you can't quite. I need to make this. Sorry about that. And now I'm going to readjust the camera focus. There we go. Hopefully now we can see the edge of my paper. All right, let's interpret our results. Let's interpret our results because we haven't done our work unless we know what we've done. We had an equation over here. I subtracted 3,480 from both sides. I did that to isolate an output by L times 439. What I'm saying is that after I've subtracted the costs of my textbooks from the total amount of money I had, I'm left with $3,020 left to buy laptops. How many more laptops can I buy, right? If I know I have to buy 30 textbooks with my $6,500, I take the amount the textbooks cost times 30, and I subtract that from the total amount of money I have. And what I'm left over with is $3,200 to buy laptops with. How many laptops can I buy with the money that's left over? Well, we divided the cost per laptop. $3,020 divided by 439. We got this L equals 6.87. Well, I know I can buy at least 6 laptops, and I know I don't have quite enough money to buy a 7th laptop because 0.87 is only 87% of what is required to buy the next laptop. So I can buy 6 total laptops. Let's look at our equation. I'm sorry, look at our options here. Number 1 is 6. That's what we want right there. We can buy 6 laptops. 7 comes really close. 7 comes really close. We're trying to trick you with adding the 7 in here. They wanted you to round up. Did you see how close 6.87 is to the number 7? But if you only have 87% of what you need to buy a laptop, are they going to sell you the laptop? No. They want you to give them the whole amount of money, right? If I go to Circuit City or something and they tell me the laptop is $2,000 and I say, well, I've got 1,600. Is that good enough? It's more than half. They're going to say, no, need the $2,000 for this laptop. Okay, I'm out of luck, right? So 6 laptops is all the math department can buy. And then I have to say the difficulty level on this problem is substantial. I'd even maybe call this one a difficult one. Yeah, I'll give it to you. Because you have to take a word problem. You have to form an equation. All right, that's difficult enough by itself. Now, the actual solving the equation, I'm hoping that's not hard. I mean, the numbers here were big, but the techniques are the same. I'm hoping you can handle that. Then you need to interpret your results. That's another wrinkle on this problem. Which I'm going to give it to you. It's not an easy one. But when you break it down, it's not that bad, right? Hopefully, we'll have to work on more of these word problems. That's why we do a lot of these in class. Number 5. All right, moving on to number 5. What is the solution to the equation 3 over 5, or 3/5, times the whole expression x plus 4/3 equals 1.04? So what's the solution to this one? Oh, golly, I'm going to need some scrap paper because I've kind of run out of space here, maybe. Do I dare? Do I dare use space for the next problem? Yeah, maybe. All right. So here's what I got to do. 3/5, parentheses. I'm just rewriting the problem. This one, we have fractions, and I know fractions scare you. I'm trying to get you to be less scared of fractions. They are still scary at this stage in the game, I understand. All right, 3/5 times x. We need to distribute. Notice this is parentheses. I need to distribute my 3/5 to my x and to my 4/3. So 3/5 times x, that's pretty easy. That's just 3/5 times x. But 3/5 times 4/3, I don't know. When's the last time you multiplied 3/5 times 4/3? Let me do it over here. 3/5 times 4/3. It's been a while since you maybe handled this kind of fraction, multiplying fractions. Well, here's how you do it. You multiply the numerators, that's the top number, and then you multiply the denominators together, that's the bottom numbers, and you get a new fraction. So 3 times 4 is 12. I multiply my numerators. 3 times 4 is 12. Now I multiply my denominators. 5 times 3 is 15. 12 fifteenths. 12 fifteenths. 3 times x plus 12 fifteenths is going to equal 1.04. Now, I would then subtract 12 fifteenths from both sides of my equation. I would then divide by 3 divided by 5. Ooh, dividing by a fraction. You haven't done that in a while, right? What I'm actually going to do, I'm going to multiply by a reciprocal. And that, as I think about it, I can do that. That's fine for me. I would actually do all this on paper. But for you, let me show you a better way for you to do it. Let me show you how I would do it right first, right? You might not want to do it this way. I'm going to subtract 12 fifteenths. And I would use my calculator for this part. Even I would use my calculator for this part. No problem with that. Minus, and I would put in parentheses 12 divided by 15. Oh, okay. Now I have 0.24 equals 3/5 times x. And then what I would do is I would times both these sides. Both sides is equal. You can't see my calculator. Can you see what I'm drawing? Oh, you can't even see what I'm writing. I apologize. So let me go over what I just said. 3 times x plus 12 fifteenths equals 1.04. I subtracted by 12 fifteenths. And I did that by putting in, no, look at that. I'm so sorry. By 104, I'm subtracting 12 fifteenths on both sides of my equation. It cancels it here. 1.04 minus, and notice I probably put this in parentheses in my calculator. I put 12 fifteenths in parentheses in my calculator. That's so important. Without that, you're going to mess up on this. And I said 104 minus 12 fifteenths in parentheses gives me 0.24. Now what I'm going to do is I'm going to multiply both of these sides by 5/3. Why 5/3, do you ask? Well, my reasoning is thus. 3/5. If I multiply 3/5 by 5/3, what happens? I get 5 times 3 is 15 in my numerator. I get 3 times 5 is 15 in my denominator. 15 divided by 15 gives me 1. By multiplying a fraction by its reciprocal is the fraction flipped. By multiplying a fraction by itself flipped, its reciprocal, I get 1, which means I've eliminated the fraction from my equation. So if I do that to both sides of my equation, here we go, times multiplying both sides of my equation by 5/3, and boom, I get 0.4. 0.4 is our answer on this problem. And then I promised you I'd show you a better way. I would do it on paper. That's me. I'm old school. You guys are the cell phone generation. Let's do this a different way. 3 divided by 5. So I have to keep my fractions in parentheses, right? Right. We have to keep our fractions in parentheses. Boop, 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 boop. All right. For this problem, here's how I recommend for you to do it. There's really no getting around rewriting the equation, distributing this 3/5 to the x and to the 4/3. You're going to be able to have to distribute this across the parentheses to get 3 times x. 3/5 times x is 3/5 times x. And then you're going to have to be able to multiply 3/5 times 4/3. But you can do it this way. You can take you can do parentheses 3 divided by 5. If you don't remember how to multiply fractions, your calculator can handle that for you, times 12 divided by 15. I'm sorry. Let me try that again. Your calculator can handle this for you, 3/5 times 4/3. 3/5 times 4/3. Your calculator can handle that for you, gives you 0.8. And you can even rewrite the equation as 3/5 times x plus 0.8 equals 1.04. That's totally legit to do it that way. Now we do 1.04. We're going to minus our 0.8. And then you're going to divide by 3/5. You see 3/5 is being multiplied by x. Well, if you tell your calculator to divide by 3/5 using those parentheses, you still get 0.4. You still get 0.4. Let me rate the difficulty of this problem here. This problem is, I'd say, medium. You have to be able to distribute across parentheses. I know some of us still struggle with that, but it's kind of one of those basics, fundamental skills that we need for Algebra 1. We do a lot of. The difficulty here was that there's fractions involved. That does complicate matters because we're not as good with fractions, but we should be able to handle that. We should be able to handle that, and our calculator can do a lot of it for us, right? We can use our calculator to do most of the fraction work for us. And then after that, it's our regular algebra skills, and it's using our calculator to great effect. So I'd call this a medium. It's not easy. It's not too hard. Again, there is that fraction work. Your calculator can do most of it if you know how to if you remember to put all your fractions in parentheses. It comes out fine. All right. Next one. The area of a rectangle is represented by 3 times x to the second power minus 10x minus 8. All right. We have a nice. Hopefully you read this and you say, oh, that's a quadratic, right? I'm hoping that by now you would say that's a quadratic just by reading it. Okay, we spent a lot of time on this kind of stuff. However, this is complicated by the fact there's a 3 out in front of there. Let me go on. Which expression can also be used to represent the area of the same rectangle? All right. All right. This is a factoring problem. We did factoring, but we didn't normally do factoring. I think I showed you some ones with 2 out in front. I don't think I've done much in Algebra 1 Prep Review with 3's out in front. So let me mark this off. 3x squared minus 10x minus 8. I need to find one of these expressions. When I FOIL it, it's going to give me the same expression over here. So I did show you some ones with 2 out in front, but never a 3, but it's pretty much the same. Why did I do this? So notice how all these, it's been simplified to a binomial. We're looking for how to simplify this into a binomial. I need to have a 3x here. I need to have a 3x here because I have 3x squared here. The only way I get 3x squared is if I multiplied 3x by 1x, because I needed to multiply 2 x's together to get x squared, and the only 2 factors of 3 are 1 and 3. Those are the only 2 numbers that I can multiply together to give me 3. It's 1 and 3. This problem, while normally we don't put 3's out in the front, the limited amount of factors there are for 3 makes this problem not as hard as it might seem at first. Then, I'm thinking about, I need these numbers here. These numbers here need to multiply to be -8. The numbers I put in here need to multiply to be -8. But they need to add up to -10. Okay? So, as I'm looking at my options, it looks like all the options they have here are 4 and 2. Are 4 and 2. I just got to figure out where my 4 and 2 belong. Well, when I FOIL this problem, I'm going to have 3x times a number. I want to get that number kind of close to my 10x to start off with. So I know that 3 times 4 is 12. That's pretty close to 10. I'm going to put my 4 there to start with. I might be wrong, and if I'm wrong, I'm going to erase this and I'm going to start over. I'm going to erase 4 and the 2 here and start over. I'm not going to start over with the whole thing. And then if a 4 goes here, then a 2 has to go here. Now I have to figure out what signs do I need where. What signs do I need where? Well, I want to get to, well, actually, let me back up a minute. I have a -8 here, which means one of these has to be positive and the other has to be negative. Because the only way I get a -8 is if I have a negative times a positive. Okay? One of these has to be positive, one of these has to be negative. And I want to get towards a -10. Remember how I made this 4 go here because 3 times 4 is close to 10? I'm going to make this a negative because 3 times -4 is going to be -12. -12 gets me close to that -10 like I'd like to get in my middle term, which means this one has to be a plus. Let me see if this works. 3x times x is 3x squared. 3x times -4 is -12x. Positive 2 times 1x is 2x. And positive 2 and -4 is -8. All right, and then -12 plus 2x gives me 10, -10x, just like I had in my original equation. So 3x plus 2, x minus 4 is our correct answer. Where do we have that in our options? Oh, it's number 1. Number 1 gives us 3x plus 2 times x minus 4. How would I rate the difficulty on this one? Honestly, I'm going to have to give this one a medium. I know it's a scary quadratic, and it's got that 3 out in front. And I know that there's factoring involved, and we're not the best at factoring. But factoring is one of those basic tools that we're working on in Algebra 1. So it's not like we haven't seen these before, seen things like it. Again, I usually put a 2 out in front of there. You saw those. Never with a 3 before, maybe. I don't know if I'd ever did a 3. But still, hopefully, if nothing else, this one is solvable by this means. You can start to FOIL these out on a sheet of paper and say, okay, 3 times 3x, okay, all that works out. I'm going to multiply my inner terms and my outer terms. 2x and -4 times 3, -12x, positive 2x, -10x. That's where I needed to be. When you FOIL these out, if you distribute across those parentheses, you should be able to see that these won't give you what you're looking for. Like this one here gives me positive 8x. That doesn't work. I can cross off 2 because I can see positive 2 times positive 4 gives me positive 8. That's not going to work. I can see this problem here, this choice here is going to give me -8. Okay, but it's going to give me a positive 4 and -6x. Positive 4x, -6x is going to give me a -2x. That's not what I want. That gets crossed off. This one's going to give me a 4x and a -4x and a positive 6x. So I'm going to get a positive 2x. That's not what I want. So this one you can actually, just by FOILing things in your head, looking for your inside-outside terms, you can quickly eliminate the bad choices and find which one is going to give you a choice. I'm going to give this one a medium. Which relation does not represent a function? Okay, Number 7 says which relation does not represent a function. Let's look at this choice here. All right, I've got 1 to 3.2, 4, 5.1, 6, 7.4. Looks like a function to me, right? So far, so good. No repeats, right? No repeats of y values. Let me see this function here. Does this pass the vertical line test? Whoop, it passed the vertical line test. That is a function. That's an absolute value function, in fact. Let's look at choice number 3. 3 times the square root of x plus 1 minus 2. Yeah, that could be a function, right? That's a square root function. We saw those briefly. Not too familiar with those. You might have your suspicions about that if you didn't know. And this one here. Can you tell me if you see a problem with this one here? Pause the video about it. Okay, we learned, we did quite a lot of work on this, that functions mean that there is one and only one output for any given x, right? Again, it passes the vertical line function, which means that if I plug 2 into this function, I'll get 1 and only one answer. That's what makes a function, is getting one and only one answer when I plug a number in. I plug a number in, I get an answer out. I plug a number in, I get an answer out. Those are functions. If I plug a number in and I get 2 answers out, we're not talking about a function anymore. This is no longer functional. I no longer know which answer to do, right? This is not a function because I plugged number 1 in and got 2 answers. I plugged number 2 in and got 2 answers. 3, I got 2 answers. This is the one that's not a function. Not a function. Difficulty on this one. I rate this one as difficulty easy, except there's a trick. You need to have the definition of a function stuck in your head there somewhere. If you don't know that vocab and you don't know how to test, not only do you need the vocab, you need to know what a function is. You need to know that there needs to be one output for every input. One and only one output for every input. Then you also have to know like how to evaluate that. You need to say, okay, I see one output, one output, one output, one out. Okay, we're good. There's no repeats of my x values here on this table. This is a good, that's how I'm looking at this table. I'm saying, okay, 1, 2, 3, 4, 5, 6. No repeats of x values. Each x value has its own y value. Perfect. That's a function. I'm looking at this graph. Graphs, I need to know, vertical line test. For function number 3, I would need to say, I've seen square root functions before. That can happen. I know they exist. I don't see any problem with that right off the bat. That's okay. And then number 4, when you see this kind of format, we're saying, these are my x values, these are my y values, and I see that my x values go into multiple y values. Not a function. Can't be done. I wouldn't call that easy, super easy or anything, but I mean, there's no math involved in terms of like calculations. There's no calculations involved. There's still math involved because you still have to be thinking up here. All right, one more. Last problem we're doing on this video, section number 8. Brittany is solving a quadratic equation. Her first step is shown below. This is her problem. 3 times x to the second power minus 8 minus 10x equals 3 times parentheses the expression 2x plus 3. And here's her first step. First step, what changed? Well, she moved the 10x over here. She moved that negative 8 over there. Remember what that property is? That like 3 plus 5 is 8, but 5 plus 3 is 8. Doesn't matter which one I add first. We can do this with multiplication too. 2 times 3 is 6, but 3 times 2 is 6, right? It doesn't matter which order I multiply things in or which order I add things in, because addition and multiplication have what's called a commutative property, right? Commutative means we can move them around. They can have different orders of community. You can move them around in any order. 5 plus 5, that's not the greatest example. 5 plus 6 is 11. 6 plus 5 is 11. It's okay. It doesn't matter which one. I can commute the problem. They can commute the numbers all around. It doesn't matter. 2, 3 plus 2 is 5. 2 plus 3 is 5. Commutative property, all right? So she did the commutative property over here. What do you remember what we call this when, what did she do? She had 3 times the expression 2x plus 3. And what did she do? She now has 6x plus 9. Well, how did she get that? We do a lot of this actually in Algebra 1. We take the 3 times the 2x. 3 times 2x is 6x. 3 times 3 is 9. We call this distribution all the time. She distributed that 3 over the parentheses of the entire expression. That's the distribution property of multiplication. All right? So our choices are, what 2 properties did Brittany use? You go to step 1. Did she use the addition property of equality? Did she add the same thing to both sides? No, she didn't do that yet. Maybe she'll do that next step. Did she use the commutative property of addition? Yeah, she did, right? She switched this 10 and this negative 10x and this 8 around, right? Did she use the multiplication property of equality? Did she multiply both sides of the equation by the same number? Nope, didn't do that in this step. And did she use the distribution property of multiplication over addition? Oh yeah, she did, right here. She did that. 3 times 2x over 6x. 3 times 3, pardon me. 3 times 3 is 9. She used those 2 things. So which one of these options do we have? She used the commutative property with 2 and she used 4. So where's 2 and 4? Boop, there it is. Choice number 4. She used the commutative property and the distribution property. All right. These are the questions 1 through 8. Hope you enjoyed this. Hope you enjoyed this change of pace, trying to switch things up. We're going to, next, when we come back from break, we're going to move right back to our usual order of business. But I thought we're wrapping up quarter 3. It's time to do some Regents review. There's still a lot of students that are, honestly, they're struggling with the Algebra 1 skills. That's okay. We're going to meet you where you're at. We're going to keep plugging at it. You can do this. You can learn it. You matter. We're going to get there. It might take us a little longer, but we're going to get there. No problem. I'm not worried. All right. Have yourself a good day.